Meet Aurion, the fifth evolution of the UAU Mars rover. Shifting from isolated subsystems to a fully unified architecture, our team of 48 members utilized a 10-month lifecycle of iterative prototyping to optimize this high-performance frame for extreme agility.
To overcome mass constraints and maximize payload capacity, we engineered a radical structural evolution. We transitioned from our legacy 6-wheel rocker bogie to a refined and lighter 4-wheel architecture. Utilizing a 4-wheel rocker suspension integrated with a spring-loaded pivot and rear differential bar. By transitioning to a carbon core hybrid design, we expanded the wheel's contact patch and diameter by 19%, yet achieved around 16% weight reduction to maximize torque to weight ratio. This optimized chassis lowers the center of mass, enabling Aurion to ascend 40-degree inclines and maintain side slope stability.
To master the increasing complexity of URC missions, we engineered a completely new kinematics architecture. We redesigned our 5-degree freedom arm with 6 custom dynamic joint units supporting a 7 kg payload. By implementing the Newton-Raphson method in our ROS-based IK solver, we achieved full inverse kinematics for fluid manipulation. This enables non-coaxial movement, essential for opening latch drawers, connecting hoses, inserting test tubes, manipulating small hand toolsets, toggle switches, push buttons, and plug-in USB-C cables. Operators seamlessly toggles between teleoperation for manual precision and trajectory control for autonomy. Integrated monocular vision maps to the arm coordinate frame to the environment, enabling autonomous keyboard interaction. To adapt to distinct mission profile, Aurion features a standardized modular interface. This architecture allows our team to rapidly swap the entire manipulator for the autonomous sensor mast or exchange the standard end effector for a dedicated science switch between tasks.
Powered by a 24-volt 30-amp-hours lithium-ion pack, Aurion delivers over 3 hours of runtime, managed by a custom BMS with remote telemetry. We utilize a distributed power architecture with a hardware-level emergency kill switch for instant cutoff and CAN bus integration for fault tolerance.
At the core is our custom-built logic board, utilizing a dual-tier compute architecture. A Jetson AGX Aurion handles high-level processing, while Tennessee microcontrollers execute low-level hardware commands.
Running on this embedded firmware, a custom Ackermann steering algorithm minimizes wheel slip, significantly reducing overall power consumption.
Powered by the Jetson AGX Aurion executes a fully autonomous outdoor mission. We utilize a traversable cost map generated from 2D LiDAR data to identify safe paths, avoiding obstacles, while EKF's state estimation combines differential RTK and IMU data for Rover sub-3 cm localization. The rover navigates to prescribed GNSS waypoint using A-star global planning. When intervened, Aurion autonomously reroutes or retreats to a previous waypoint and replans. Inside the search zone, Aurion switches to GPS view systematic search pattern. Using ZX stereo vision, we detect and track Orogo marker on posts and utilize YOLO-based object recognition to identify mission targets, a pick hammer, wide-mounted bottle, and orange rubber mallet. Upon successful arrival at the checkpoint, the system highlights the target on the operator dashboard and signals arrival by activating the flashing green LED indicator.
We achieved a perfect science score last year, but we wanted to push our in-situ analysis further. To do this, we engineered a deployment mechanism for our Raman spectrometer probe enabling direct contact measurements. This augments our advanced sensor fusion system, which analyzes 7 soil and 7 atmospheric parameters to narrow down sites using an automated decision algorithm. For extraction, our dedicated regolith collector drills and caches samples from depths of up to 15 cm and features a quick-release caching mechanism for rapid handoff. Sample retrieval is powered by our modular Rover manipulator, which precisely delivers it to the wet lab by frost. Here, samples are analyzed for carbohydrates, proteins, ammonia, and chlorophyll using Benedict's ninhydrine, salicylate, and UV fluorescence. Fully isolated zones prevent cross-contamination, while a 4K panorama camera captures stratigraphy, all logged to the dashboard in real time.
For mission-critical connectivity, Aurion establishes a high-bandwidth dual-band link operating on 2.4 and 5.8 GHz and a telemetry link on 915 MHz. This architecture delivers a validated 2.5 km range, maintaining high throughput stability for 4 simultaneous camera feeds, dynamically balancing low-latency navigation and high-resolution sense feeds. Verified across varied interference scenarios, this system ensures uninterrupted command and control across all competition tasks. For extreme delivery, our drone Aurion B utilizes a 3-axis gimbal-stabilized 4K optical payload to decipher distant signage and identify mission objects.
With over 80 hours of extensive drive time and a complete architectural evolution, the UAU Mars rover team has refined Aurion into a resilient mission-ready platform. Moving beyond the lab, we have rigorously validated our hardware across simulated Martian environments, conquering deep regolith trenches, aggressive rock gardens, and high-vibration terrain. Through relentless iterative testing and strict failure analysis, we have engineered a system built specifically for the unforgiving conditions of the Mars Deserts Research Station. We are prepared to push the limits of exploration. We wish all the participating teams the best of luck. See you in Hanksville this summer.